Here in Chapter 17, we'll be looking at carboxylic acids, esters, and amides. In the picture here, you can see the leaves of a coca plant, and from that can be extracted cocaine. The structure contains two esters. Cocaine, as you may know, is an addictive stimulant. If we look at the general structure of a carboxylic acid, we have a carbonyl, which is that C double bond O, and that's connected to the OH here. So that's our carboxylic acid. And we can see a simple one there in gray. C double bond OH is our carboxyl group. And this is a common one, that's acetic acid. Acetic acid is not the IUPAC name. That would be ethanoic acid. But commonly, if you have an R group with this carbonyl and a CH3 here, this is known as an acyl group. And that's where we get acetic acid from, or acetaldehyde. In an ester, the general structure is the carbonyl again, and then instead of the OH, we have an OR group. So this carbon group here, this is an ester. And a common ester is methyl acetate. If the ester shows up in a ring, this is called a lactone. So that is another name for a cyclic ester. This is the general structure of an amide. That R prime there can be hydrogen or an alkyl group. So you can have two hydrogens there, or you can have one alkyl group and one hydrogen, or two different alkyl groups. If you have just hydrogens on there, this is a primary amide. So it has one CN bond. If you have one R group here, this makes it a secondary amide, because we have two CN bonds, which are shown there in red. And then if you have two R groups, this is a tertiary amide with three C to N bonds. And then anytime you encounter a cyclic amide, that's called a lactam. The bond angles in carbonyls, if you recall, are 120. And because that carbon is bonded to three atoms, the shape here is trigonal planar. And then this is a polar bond. We have a partially positive carbon to a partially negative oxygen, so that makes it polar. Esters we'll find quite a bit in nature, in essences, in fragrances, and flavors. One ester that you might find in a pear is propyl acetate. So you can see the C double bond O in red, and then the R group here is this propyl, and then we have the acetate part of that. This is an ester. We might find oxalic acid in spinach leaves. These are carboxylic acids. And capsaicin comes from chili peppers, and that has an amide functional group here. We also have an ether. And then you know about the alcohol here. So we're going to draw out a couple structures here and decide if it's a carboxylic acid, an ester, or an amide. So I have a C double bond O2 with a CH2, CH3. I'm going to start with the C double bond O. So there's my CO2. That is C double bond O. And then I have a CH2, CH3, and then on the other side of that oxygen, there's a CH2, CH3. So this is an ester. And then we have here a CON. This is my CON, so this is going to be an amide. There's an H on that nitrogen, and then a CH3, and on the other side, there's a CH3. This is an amide. Here we're supposed to label each functional group in lisinopril, which is a drug used to treat high blood pressure. This drug actually lowers the blood pressure by lowering the concentration of the polyamide angiotensin in blood. For part A, we're looking at functional groups. CO2H is a carboxylic acid. This N here is not connected to a carbon double bond oxygen, so this is an amine. but this one is. This happens to specifically be a tertiary amide. There are 3 CN bonds coming off of that nitrogen, and this one right here is a carboxylic acid. And I see we have one more amine. The next question is asking us how many trigonal planar carbons does lisinopril have? And that's going to be anywhere C has a double bond. So this one here, this one, and then all the ones in the benzene ring are also trigonal planar. When we name carboxylic acids, the longest carbon chain has to contain the C double bond OH group, which can also sometimes be written as CO2H, which we saw in the last slide. We change the E ending of the parent alkane to the suffix oic acid. The other thing is that the carboxylic acid group is always going to be at C1, but we don't use that in the name, and then we're going to apply all other rules. So there's a couple of common names again. I'll give you the IUPAC name and then the common name. If we have one carbon, this would normally be methane. I drop the E and use oic acid, so it's methanoic acid. And sometimes with that one carbon, this is commonly called formic acid. And this is the acid that is formed in the metabolism of methanol. 2 carbons would be ethane. I drop the E and use oic acid. This is commonly called acetic acid. If we have the carboxylic acid on a benzene ring, this is benzoic acid. And then for the longer chain, this is my carbon chain. This is at carbon 1, 6. So I have 4, 5 dimethyl hexanoic acid. And I'm going to find my longest carbon chain here containing the carboxylic acid. So this will be 2-ethyl 3-methyl pentanoic acid. So here's a couple more practice problems. We have 2-ethyl 5,5-dimethyl octanoic acid, and we're going to draw these. So octanoic acid tells us we have 8 carbons, and C1 is at the carboxylic acid. So this is 1, 2, 3, 4, 5, 6, 7, 8. I have an ethyl at 2 and 2 methyls at 5. And then valeric acid and isovaleric acid are common names which you're not responsible for, but these acids are associated with the odors that come from unwashed feet. So you can imagine that they're not very pleasant. Extracts of valerian, which is a flowering plant, contains valeric acid as well as this isovaleric acid, and these were used as sedatives in ancient Greece and Rome. It's also thought to be used as a dietary supplement to treat sleep disorders and anxiety, although its efficacy is unproven. So if we're going to name these, this is my long carbon chain. There's 4 carbons, so this will be butanoic acid. This has 5 carbons. There's 3-methyl butanoic acid. When we name esters, the arg prime group bonded to the oxygen atom is treated as an alkyl group. For the ester side, we drop the ic acid ending from the carboxylic acid parent and then use the suffix -ate instead. For a CH2CH3, that's 2 carbons, so this is an ethyl group. This would be ethanoic acid, so I drop the ic acid part, so it's ethanoate. This one can also be called ethyl acetate. If you have 1 CH3, this is methyl, and for a 4-carbon carboxylic acid, this would be butanoic acid. So I'm going to name this one methyl butano. I drop the ic acid and end it in -ate. So that becomes methyl butanoate. So we start with the side that's the oxygen. So this is a propyl group, and this will be pentanoate. So we drop the ic acid from pentanoic acid and then end it in -ate. And on this side, this is my group that's on the oxygen side, so this will be cyclopentyl ethanoate. Or you can have cyclopentyl acetate. Either of those would be correct. For naming amides, we're going to start with the alkyl groups just like we did with the ester, except we're going to use an N in front of that so we know where the alkyl group starts. It's kind of like using numbers in an alkane chain. And then we end our name with amide. So when we name primary amides, this would be ethanamide. So ethane, and then it ends in amide or amide. This one's also called acetamide because of this acyl group here. That comes from ethanoic acid. We dropped the oic acid and ended in amide, so ethanamide. This would normally be benzoic acid if it was a carboxylic acid. So we dropped the oic acid and ended in amide. If you have a group on the nitrogen, you start with the alkyl group here. So I use N. There's 2 carbons, so this is ethyl. And this would be methanamide. Or you could use N-ethyl formamide. That comes from the formic acid. And if you have 2 R groups, this will be N-dimethyl. And then instead of benzoic acid, this will be benzamide. So we can practice drawing a couple of these here. So butyl benzoate. O8 tells me I have an ester. The benzene tells me I have a benzene. The carbonyl side is coming off of that. And the butyl is the carbon coming off of the oxygen. So I have 1, 2, 3, 4. For decanoic acid, the oic acid tells me I have a carboxylic acid. There's 10 carbons. This is 1. Pentamethyl. I have methyls at 1, 2, 3. There's 2 of them. 4 and 5. Ethyl formate is the one that has 1 carbon. There's a hydrogen on this side. It's an ester because of the 8 ending. And then there's an O here and then ethyl on the other side of that. Ethyl formate is one of the contributing characteristic flavors of raspberries. And then pentanamide, I have an amide with 5 carbons, 1, 2, 3, 4, 5. And it says N-ethyl and propyl. So on the N, I have an ethyl group and also a propyl group. Carboxylic acids are capable of hydrogen bonding, which means that they have high boiling points. So they actually have more hydrogen bonding possible than alcohols do. So the boiling point of this compound here, this is methyl ethanoate. This is an ester. We can't hydrogen bond with an ester, so the boiling point here is 58, so there's no H bonding. But a similar sized carboxylic acid has hydrogen bonding, so H bonding here. So the boiling point of this one, which is called propanoic acid, is 141 degrees. So the boiling point is much higher once we introduce that carboxylic acid into the structure. If we look at propanol, our alcohols, which used to be our highest boiling point, that boiling point is 97. And a similar sized acetic acid has a boiling point of 118. So there's more hydrogen bonding here. Between an ester, a tertiary amide, and a primary amide, this one has hydrogen bonding possible. So on the primary amide, we're going to see the highest boiling point. So for the ester, it's 58. So for the tertiary amide, it's 153. And for the primary amide, it's going to be 213 degrees. So that one has much more hydrogen bonding capabilities. It has the carbonyl, and there's 2 hydrogens on the nitrogen, as well as that lone pair, which can hydrogen bond. So if we're going to compare carboxylic acids to aldehydes, Carboxylic acid has hydrogen bond capabilities, so that will have the higher boiling point. And between the amide and the ester, it's going to be the amide that has the higher boiling point, again because of hydrogen bonding. Simple carboxylic acids tend to have terrible smell. Formic acid is responsible for the sting of some biting ants. Acetic acid is our sour tasting component of vinegar. So sometimes that smell slaps you in the face. That is that acetic acid. The oxidation of ethanol to acetic acid will also make wine have a bad taste associated with it. Butyric acid smells like baby vomit, or some people smell it as rotten butter or Parmesan cheese. Hexanoic acid is the smell from dirty socks or a locker room. It also contributes to the unpleasant smell of ginkgo seeds, which are shown up in the picture there. So the common name for hexanoic acid is caproic acid, and this is derived from the Latin word caper, which means goat. These ginkgo trees have been around for 280 million years. Their extracts have been used in China, Japan, and India for medication as well as for cooking. We're going to see carboxylic acids in skincare products. Alpha hydroxy acids react with the outer skin layer, which causes the skin to loosen and flake off. So these products actually do not reverse aging, it just removes the old skin to bring forth the skin that was underlying there. So the general structure of an alpha hydroxy acid is one that has the hydroxy group, or this alcohol, on the carbon next to the carboxylic acid. So glycolic acid and lactic acid are examples of alpha hydroxy acids. Other places we might see carboxylic acids are in aspirin and other inflammatory agents. Aspirin, as you may know, relieves the pain and decreases inflammation. It also blocks the synthesis of prostaglandins, which are responsible for physiological responses. So if we have aspirin, which has the carboxylic acid here, it also contains an ester. Ibuprofen has the carboxylic acid. And then naproxen also has this carboxylic acid. So those block arachidonic acid from forming prostaglandin PGF2 alpha. PGF2 alpha and similar compounds cause pain and inflammation. So if we can block that process, then we won't feel the pain. We're going to encounter lots of different interesting esters and amides in smells. One that we see here, which comes from mangoes, is ethyl butanoate. From apricots, we might see pentyl butanoate. From wintergreen, which is a precursor of aspirin, if you wanted to synthesize aspirin, you can do that from wintergreen, which has the common name of methyl salicylate. Melatonin is an amide, and that is synthesized by the brain's pineal gland, and it's thought to induce sleep. Melatonin levels in the body arise as less light falls upon the eye and drops quickly at dawn. So our melatonin levels increase as it gets darker and then drops quickly in the morning. Benzocaine is an ester, and it's used as a local anesthetic. And then we have acetaminophen, which is an amide, which has a common name of Tylenol, which is used for pain relief or fever reduction.